Hi, this is a presentation video for Urban Mobility Sandbox project. More specifically, it is a case study of the NYC subway recovery after COVID-19. First, let me recap on the backgrounds for this problem. Today's NYC subway is experiencing a dramatic drop in ridership after the COVID-19 pandemic. The subway system needs to know how and where the ridership is coming back to better plan the future for the subway system. To do so, I collected this data set to facilitate the modeling of ridership. This includes different kinds of data, including the subway ridership itself, the loads data, which is demographic data about where people go to work and where people live, Uber mobility for traffic speed, facilities data set from the municipal government, as well as other features. More specifically, I want to do a high-resolution data so that we can understand the features relationship to the subway in a higher temporal and spatial resolution. Since the data I have better coverage during the year from 2019 to 2021, I use this time horizon as the main study period. For the spatial and high-resolution data, I did some cleaning in addition to the current data. This includes matching the different station complex and turnstile data together, building upon the existing work by many other data hackers, civic hackers that have been playing with the data. I also added some of my own innovation. Instead of using rule-based system as previous study did, I use data-driven methods to assign the different volume data to each hour, increasing the resolution of the subway ridership data. The data is now ready in the analysis-ready format, and I have already shared this with my friends at the GSAP of Columbia, and they have applied this data in their own analysis of who are left out during the lockdown period. So for feature engineering, we just look at the different source of data. I chose these 5 main source of data during the analysis because they represent different aspects of the transportation problem, including demographic features, alternative modality features, location accessibility, amenity and attractions, as well as non-spatial usage habits. For each of those features, I applied custom feature transformation based on the nature of that data, and also spatial aggregation based on the spatial coverage and their relation to the subway station. Let's take one quick look at one of the feature, Uber movement data, which is traffic speed data, which I use then to measure the congestion level in a certain area. If we look at the data itself, we can see that it is a time series at hourly level of how fast the traffic flow goes on each street segment. These two streets might seem similar at the first glance, but if you normalize the speed by the free flow speed and see how much slower the busiest hour will be, you will see that these two streets actually have different congestion level. This translates to a different feature space once we map it on the overlay of NYC map. We can see that if we use absolute speed, the difference is actually not very pronounced, but if we used this relative speed, we can clearly see where the congestion is more serious. We then can match this feature's value to different subway station complex, and we can do so by creating different isochrones, which is catchment areas around the different stations. Traditional methods might be using a distance-based catchment method, but in this scenario, I use a street network and the walking distance of 5 minutes to 10 minutes as a way to create a more realistic measurement of who can reach the station. With that data, we then consider the different entrances of the same station and merge the different isochrones together to create a catchment area for each station. With that information, we can then match the different values to each station. Here we have a visualization of matching the different congestion level data to the different catchment. We can do the similar thing for different city blocks. Once we have a catchment, we know which city blocks are covered by that catchment, and then we can link the different demographic data of each block to the different stations. Here in the background, we see a density of the young people working in the city where they live. This data can be presented in a density format or proportional format, and all of those can be linked to a substation using the isocross. When it comes to predicting the subway ridership, there's many ways to actually measure the subway ridership. We can measure the level of ridership during the weekday, during the weekend, or even just during the rush hour. In this project, I explored different metrics and ended up using the rush hour hourly ridership as a proxy for how busy a station can be. I first used linear regression as the baseline, and the features are just the congestion levels, usage habits, all those features we just described in the feature engineering part. We can see that the MAE, the mean absolute error, for the linear regression model is about 400 person per hour, which is pretty high, and R-square is only 20%. When we switch to a more expressive XGBoost regression model, we managed to cut the MAE by half, and now the R-square is also 70%, which explains the 70% of the variation in the data. To explain why the model is reaching at the conclusion or the prediction they make, I use sharp value visualization to break down the prediction for single stations. We can see that here for 50 streets, we can see that because this location have more parks, plazas, and also transportation facilities, the prediction is higher than average. While in comparison, Wicklow Avenue sees a much lower ridership because it has fewer facilities for transportation and also less flow size, which is a measurement of people who can use this station to reach their place of work. We then plot the different contribution of the different features to the final model output. We can see that the most important or the feature that contributed the most to the prediction is the number of transportation facility. This includes parking lots, bus terminals. So it is important that people can actually reach the places, but it can also be interpreted as the places are transportation hubs, so there's overall higher ridership. We also see that historical sites, libraries, and parks are also attractions for the ridership. An interesting observation is that when we look at some of the less significant contributors, we can see that people who are in a production kind of work tend to take the subway more. We can also see that when the congestion level is high, people tend to use subway also less. This is interesting because we might guess that congestion level is high indicates that people might turn to subway to avoid the traffic jam. Further analysis needs to be done to understand what really happened. We also see that bicycle-friendly road seems to predict better ridership, which might suggest that people use bicycle to go to the subway stations. We then look at the recovery rate of the morning commute as an example to see how different demographic patterns may contribute to different recovery rate at different locations. Here we use the ratio of the third quarter average morning commute ridership over the third quarter of the 2019. Similarly, we see an improvement of the prediction power by switching from linear regression to XGBoost regression. This time, the different factors are at work when predicting the level of recovery for different stations. We can clearly see that when we have more professional and finance industry workers, the recovery rate tends to be lower, while when there is more human service accommodation and retail sector residents living in the area, people tend to go back to subway sooner and more. This result is again visualized in the shop value summary plot. An interesting note is that we also see that education attainment seems to predict the average recovery rate of that location. When the people are more likely to be high school educated only, the recovery rate is higher. But when people have an associate degree or higher, they are not going back to subway station as often as the other areas. This seems to suggest that people with higher education level will have a bargaining power when discussing working from home policy. So that's the presentation for this project. If you have any question, you can reach me at the email below.